Stuff already. John explained it. And after me comes Manville, who will deconstruct everything we have to say. And it's very good. I mean, it's very worth thinking about. And I will address two disparate audiences. You know, I'll try to give to people who have no experience in periodic orbit theory some intuitive feeling, you know, how it works and why it might be applicable here. And then I have to address my colleagues who actually work on this and discuss the symmetry, importance of symmetries when you use this invariant solutions. And that's a little bit tedious, but you know, that's the real life. And that's what I'll do. So the kind of intellectual driving thing is that when we look at turbulence of moderate kind, we don't see infinite range of scales. We tend to see large coherent structures. And the question is, you know, can we develop, if you're a dynamical system theorist, can we develop a vocabulary of this and make the statement precise? So that's what this work is doing. That's why we are looking at various exact invariant solutions, because they enable us to do this, and we can make the statement that, you know, we are walking through a space of such unstable patterns rather precise. What John and myself and Jonathan Halkora and other students have achieved so far, and of course, you know, people before us, starting with Nagata and Carswell-Acker, etc. We now have a chart which is not, you know, you look at an individual solution, but we have a chart of totality of solutions that we know so far. I mean, we only know subsets of solutions, and of course, there are infinitely many unstable periodic orbits, etc. But even for equilibria, which there is a finite number, we don't know how many we got, but we are fairly confident that we have gotten stuff that turbulent behavior in this moderate turbulence in small boxes explores, and this is one thing that we have. So, you know, there are every dot is an equilibrium solution. The dotted stuff is typical turbulence, so it says it's being ushered by this set of solutions. There's some kind of rigid frame, there's some traveling wave solutions and stuff like that. We also have some inkling of dynamics. You know, every one of these invariant solutions actually doesn't participate in turbulence, because if you're on equilibrium traveling wave, nothing happens. You know, things are the same forever. But what you really care about, they're all unstable. So you care about, as you're kicked out from one neighborhood, how you land in the other neighborhood and how you wander around. And you know, thing that totally blew me away is that it's actually possible to compute heteroclinic connections with these various solutions. So here are some examples of heteroclinic connections, and you know, John has illustrated, which means that from this neighborhood I can go there, and from there I can go someplace else, which tells you that we can start making coarse symbolic dynamics of which letters of the alphabet are these equilibria that we are showing you pictures of. And the dynamic says I can go from here to there, to there, to there. And that is, you know, prerequisite of dynamical systems description of chaotic or ergodic or turbulent sets, meaning that I'll be able to describe all possible motions qualitatively, and then I'll be able maybe to do some quantitative predictions. So that's what we have so far. And then this is, you know, we are supposed to be able to talk to each other, except as far as I can tell, we are talking all the time in the seminars. But, you know, we have this discussion time. So I would really love to discuss, you know, what are we going to use this? It's rather painful to do this. And there's nothing universal about this. In every particular problem, you have to work this out. You know, different for pipes, different from channel flows, for different Reynolds number, different this and that. So it's only worth doing if you really want to actually do something with it. I mean, so far it's a conceptual exploration. You know, it's a wandering through very high dimensional space. Dimension meaning, you know, your discretization of PDE. But we would like to use it. So what I'll explain is, you know, how we get long time averages out of this, how we predict quantities you might want to measure or care about, like dissipation and power that has to be put in to maintain the motion. You already seen that the solutions that we have, they're not, you know, like solitons in a sense. They don't describe pieces of what you see. All of them are global solutions. Every solution that we have has a boundary layer, you know, has a big motion in the middle and stuff like that. So they are they cover all the scales and all the Fourier components available at that particular small transitional state of fluid. I won't spend much time now. What I would like to talk to you about is, what are we going to use it for? So it might be useful to use it as a theory of turbulent Lagrangian mixing, because now we have a rather detailed understanding of what the velocity fields are doing in time. We might want to transport some passive scalars like heat from surface to surface. We might care about, oceanography. We might care about control, because now we have a very detailed, what John didn't show you, he and Divakar and other skillful people can compute not just the states of the fluid, but also the eigenvectors of perturbations. And that means that there is a way to perturb entire bulk of the fluid in such a way to move it someplace, like back to the state or away from it. So, we might be able to implement rather detailed control, and experiments are being built up like this. So Mike Schatz is building an experiment at Georgia Tech to do this kind of things. That might be possible. And then, something which you might find a little bit weird, but suppose that, you're an Earth physicist and you have about zillion terabytes of data of cloud cover of the Earth. And what clouds are, there are some shapes that are someplace on the surface of the Earth, and you want to give them names. Now, that means that if I can say this is a Syro, this is Strato, etc., and if I can quotient out translational symmetry, this might be a very effective way of dealing with turbulent data, because I can do some very expensive calculations to get the vocabulary right, and then I can try to analyze data in these terms. I'm very interested in talking about it. And I'll go to the first thing on this list, how to do long time averages. This is done by trace formula, and that's what gives mathematical physics very bad name in a group of people like this, because there's no way in the world that you can understand what this formula means when I give it to you, but it is actually how you do it. I'll give you just a little bit of a qualitative feeling, what does this formula mean? And basically, the issue in flows like this, chaotic, turbulent, which are exploring relatively small portion of state space, is that the state space, here drawn as some kind of two-dimensional surface, gets partitioned by kinds of behaviors and the neighborhoods of these behaviors. So once you have, for example, a periodic orbit, it's something that appears after every 60 unit times of your simulation, but there is a whole neighborhood of it which behaves similarly for that time, as John illustrated in the shadowing simulation. And then there are other neighborhoods. And the idea of periodic orbit theory is that you try to exhaustively go to some resolution in the state space, and do job as well as you can. And sometimes it's amazingly good, because it turns out a few periodic orbits, if you use that unintelligible formula before, might give you super exponentially accurate answers. So sometimes the thing works like charm, but that's not the point of this talk. And what's the basic idea? If you're in a neighborhood, if you look at linearized flow, what it does is it takes a ball and maps it into an ellipsoid. And the only thing that's important, and that's why we can do this in turbulent flows, is that unstable directions are what you have to worry about. You have to worry about directions where your neighbors run away from you. And there could be 60,000 stable directions. They're all bunching toward you, and that's nothing that you need to control. So the only thing that's important are the unstable directions. And that means when you have exact recurrence, the only thing you care about is how much of the original cigar overlaps with what you started. This is measured by expanding eigenvalue along the eigenvector of linearized flow, which Divakar and Gibson can compute rather accurately. And this eigenvalue, if it's larger than 1, tells you the fraction of the guys and girls who stay in the neighborhood after one return. So that's the meaning of trace formula. It says locally, you're finding how big is the neighborhood, and it's only determined by the unstable directions of the flow. then when you think about it, there's a little bit more to it. You know, if you take a long time to come back, that's going to be less important. So basically, the state space gets partitioned into neighborhoods. Each neighborhood cares about, you know, exponentially how long it takes you to come back. So this is cycle period. And it cares about how unstable is the product, the volume that's spreading out, which is given the product of expanding eigenvalues. So this is the size of the neighborhood in the original picture that I gave you here. If you ask yourself what this means, you know, what are these neighborhoods? They're given by that. And the wonderful thing is, if there are only 3 unstable directions, it could be 60,000 directions, it doesn't matter. The theory applies for that. Then there is, you know, fancy thing about shadowing, which says that if you have recurrent flows, there are shorter periodic orbits that shadow for a time your longer one, and you should use this intelligently, and that's why one has to develop these trace formulas. They build in shadowing automatically. So when you do calculations, you don't just look at an orbit, but you also look at this so-called pseudo-orbits, in which you for a while follow something, then you hop, you follow something, then you hop, and you subtract shadows. That's why -1 is here from the longer cycles. And once you have this, then you can compute anything which is a long time average in the flow. So for example, if you care about dissipation, what you do is you compute it on every solution. So laminar solution has dissipation 1, but some turbulent solution has dissipation rate 3.7, etc. You compute it on every periodic solution. So this is your, you know, computation. Then you give it this weight, how important it is. And these weights are exponentially small, so you can truncate your expansion and get very accurate answers. So that's why, you know, sometimes 10, 12, 100 orbits give you extremely good answers, even though there are infinitely many periodic orbits always in hyperbolic flows. So that's the idea of periodic orbit theory. And real calculation looks, you know, you look at some very short motions that are the most important things. It turns out the shortest periodic orbits are really important. The other guys get shadowed, and, you know, they get exponentially suppressed. And that's how the theory works. And it's not so mystical when you see it this way. And, you know, once you develop technology for finding these periodic orbits, this will work for you. It works for us. And here's an example which is due to Kawahara. This calculation, you know, is John Gibson's, but the original thing was Kawahara and Kida in 2001, 2002. They were the first to find unstable periodic orbit in a real Navier-Stokes flow. You know, I found this totally amazing because I didn't think I would see this in my lifetime, because this is a very difficult calculation. And, you know, that's what motivated all our research since then, the fact that this is actually possible to do. So, you know, in detail, this is not exactly what's going on, but basically, you pick out, you know, one of the typical periodic orbits. It's embedded in turbulent flow, meaning you visit it most frequently, and you compute for it the mean velocity profile, and it's insanely good. And you compute for it, you know, velocity square or Reynolds stress, and it's still insanely good. So, you know, that led to Japanese heresy of saying that there is a magical unstable periodic orbit that gives you all answers. And that's not quite right. I mean, you're very lucky here that, you know, one orbit gives you answers that you care about. Maybe not all, but these averages work out. Well, the theory says you have to look at hierarchy of them to be sure about convergence of the thing, etc. So this is, you know, evidence that periodic theory is applicable, even though it was developed for quantum chaos and it was developed for low-dimensional dynamics. You know, it wasn't meant to work in turbulence. But for these transitional flows, it seems to be working rather well. So this is the, you know, I hope you understood something about these periodic orbits. They're useful if you can find them. They're rather hard to find so far, but you can download channerflow.org from John's website, and you can go home and do it. But, you know, it took a while to develop this. I think it's kind of maybe already doable. I mean, we have undergraduate students who can use this. So how am I doing on time? 4 minutes. So now there is a technical thing, which is next 20 things, which I'll go very quickly through. Navier-Stokes always has, you know, these settings have symmetries, and There are various kinds, flips and translations, and there are physically important ones that you saw before. And the symmetries means that you can see something 4 times, or in the state space, the upper branch is seen 4 times. And that's a little bit annoying, and especially annoying when you look at fluids. So I'll give you an example how you get rid of the symmetries. So for example, Lorentz flow has a symmetry rotation by pi, but you can remove that symmetry by changing your coordinates, polar coordinates, and you can make it something that doesn't have the symmetry. That's called quotienting flow desymmetrizing. Here it's not such a big deal, but it's kind of cute. That means when you look at Poincaré sections, something that's here is repeated here, and the symmetry just makes one copy of that. It's much more annoying when you have traveling waves and continuous solutions. There what happens is everything drifts on you. So this is an example of a 5-dimensional flow. Everything is drifting. And you can desymmetrize this. You can quotient out rotations. When you do this, you get a very simple thing which looks like Lorentz before. Once you have this, you can construct a Poincaré section of it. And you can study the motion, what happens to the unstable manifold in one return, and get a return map. Now, what's important about these return maps, unstable manifolds are low dimensional. So even though we're in 60,000 dimensions, there's a natural coordinate along which we can measure, and low dimensional coordinate along which we can measure recurrences. And we can then, if we find maps like this, we have done it for Kuramoto-Shiroshinsky. We haven't succeeded yet for Navier-Stokes. We can find incredibly good description of very complicated turbulent flow because it reduces essentially to one-dimensional dynamics. So here, in one-dimensional PDE, we were able to find thousands of periodic solutions systematically, hierarchically, by using intrinsic coordinatization in terms of unstable manifolds. Then I'll finish with a bang. Once you do this, you realize you have to modify your periodic orbit formulas. The trace formulas take some more obscure form, where it starts looking like quantum mechanics. Characters of groups show up, and the formula gets weighted by characters and whatnot. And this is the end of my talk. We almost made our students beautiful, but we succeeded only halfway. So this is Jonathan Halcro, who did some of this work, and this is Paris Hilton. And but if you would like to know in detail how this works, please go to chaosbook.org. On tutorials, we have John's talk done in such a way that you can do it yourself at home just by clicking through the movies. And the periodic orbit is explained here, and it's for free. All right.
Something, a kind of placebo of the diagnostic method. You talked about the resemblance between the turbulent simulation and your periodic orbit. Now, one would like to rule out that that's merely kind of a gross property of anything at that Reynolds number. How could you do that? How could you, I don't know, but how could you imagine having a simulation that didn't resemble a periodic orbit, one of your periodic orbits, and how would you, could you deliberately produce something that didn't resemble a periodic orbit and show that your method distinguishes between resembling a periodic orbit and
later. Not? In a little time, but idea is if we manage to produce this hierarchy of orbits, we explored fully some part of the state space, and it should be exponentially accurate. So typical ergodic orbit should be, but there could be all kinds of stuff we are missing. Absolutely.
Any more questions? Yes.
Well, I have kind of a, I don't know, more general practical question. So if I tend to believe that we have something periodic in time and that's all fine, and this is, if I go back to the movie I showed earlier in my talk, we saw this glance of something periodic, but then it stops. So what do we do with space? Why are these, the things we see in experiments are always localized, so they tend to resemble a traveling wave or something And I can look downstream and I see the same thing again, but it's still limited in space. It's always, I don't know, a couple of diameters long, but not longer. And this is
Well,
something.
Björn Hoff is going to build an experiment in Göttingen on Planck, but we'll be looking at the thing like that. So yes, these solutions that he showed you, John showed you as periodic in space and time, and that's really weird because you never see this, right?
Right.
But you never actually see an unstable periodic orbit just in time, and we've gotten used to this idea. The idea is that locally you visit them, and they're giving you patches, but of course they're exponentially weakly correlated as you go further away. So you could think of them as a local path. It doesn't matter as long as you have a window of resolution on which you compare this pattern in space and time within some accuracy. Then we're okay.
Okay.
Trust me.
We'll stop here. Thanks very much.
That's good.